So welcome back everyone. So in today's video, we'll look at two problems from electric circuits. So in the first question, we have a circuit where all the elements are ideal and the key over here is actually open. So in the first question, we have to figure out the current I10 through the resistor of resistance 2R when the key is actually open. And this question is pretty straightforward because initially they're of course talking about the steady state, and in the steady state, if the current in this branch is I10, then I10 does not change with time. And if it does not change with time, the voltage drop across the inductor is just 0. And the story with the inductor of inductance 2L is also the same. So basically this is just a simple, resistance circuit. So we can just figure out, so the R equivalent would be, so the 2R and 3R are in parallel. So their equivalent would be 6R by 5, and they are combinedly in series with R. So it will be 11R by 5. So let's say the current leaving the battery is I. So I would be equal to 5E divided by 11R. So now we can do the parallel division formula. So we have two resistances in parallel. So the current through this branch will be equal to the resistance of the opposite branch divided by the sum of their resistances. I10 would be the total current, which is 5E by 11R, multiplied by the resistance of the opposite branch divided by the sum of the resistances, which would be 5R. So this is nothing but 3E divided by 11R. Okay, so this is the answer to the first question. And in the second question, okay, so now we are going to close the switch. Okay, and once we close the switch, they're asking the rate of increase of current in a coil with an inductance of 3L immediately after the switch is closed. Okay, so let's say the current in this branch is some I3L. Okay, so now right after we close the circuit, the current through the inductors cannot instantaneously change. Okay, now there is an exception to this particular rule, which we'll explore in the next question. But for the usual problem where you simply have a resistance and an inductor attached to each other, suddenly after switching, there cannot be an abrupt change of current. So the currents in the branches containing the inductors, they will be exactly the same as before. So what that implies is that the current I that is leaving the battery right after switching is still going to be the same. So now what we can do is we can figure out the potential difference across the inductor containing branch, which is once again going to be the same as the potential difference across the branch containing the battery. So that delta V is nothing but E minus IR, and IR would be 5E by 11. So this is going to be 6E divided by 11. Now this 6E by 11, okay, so now basically just apply KVL in this loop. So the voltage rise in going from the resistor to the EMF to the battery is 6E divided by 11, and that should be equal to the voltage drop across the inductor. So we can say 6E by 11 would be equal to 3L I3L dot. Okay, so from here I3L dot just comes out to be 2E by 11. Okay, so that was the answer to the second question. Now for the third question, we have to find the charge that will flow through a resistor with a resistance of 2R when the switch is closed. Okay, so as we have to figure out the charge, we'll just say the current through this branch. The general function is some IL. Okay, so let's think about the initial situation and the final situation. So initially we know that the value of IL is 3E by 11R and I3L is 0. Now what happens finally is that of course the inductors will replace it by conducting wires, because the currents in each of these branches would have achieved a steady state. The I dots in individual branches would be just 0, meaning there won't be any voltage drop across the resistance, across the inductors. So what that means is, if you observe in this branch, there is no voltage drop. So basically it's kind of like short circuiting these two resistors. So finally, the total current leaving the battery would just be E divided by R. So we can just write it down over here. So I3L final is just E by R. So we know the initial and final currents in the I3L and IL branch. So we can just write a KVL expression in this branch, okay, containing the inductor L and the inductor of 3L. So let's write it in the counterclockwise sense. So potential drop across the inductor is IL into 2R. So minus IL times 2R minus L, IL dot, and and now if we go in this direction, the voltage across the inductor is plus 3L, I3L dot, and this should all add up to 0. Okay. So now this is the equation that we have to work with. Okay. So now what we'll do is, of course, integrate with respect to time, because we want the charge, right? So integral of I dot dt is just the change in current. So this is just the change in I3L. Integral of IL dt is the total charge that flowed in this particular branch, okay, which is what they're asking. This is just the change in the value of IL. So the final value of I through 3L is E by R, and the initial value was 0, and through the inductor of inductance L, final value would be 0, and initial value is 3E divided by 11R. Okay, so now we can just solve for delta Q. So after solving, the answer comes out to be 18 LE divided by 11R squared. So yeah, that was it for this question. Now let's move on to the next one. Okay, so in this question, we have this particular network, and at time t equal to 0, we turn the switch from position 1 to position 2. Then we have to find the current after switching and the current as a function of time. Okay, so this problem is quite different to the previous problem. So first of all, the active circuit is this particular circuit, and we can easily find out the steady state current right before switching. So before switching, we'll just convert this into a plain wire, and the current is just going to be 5 amperes by Ohm's law. So the initial current here was just 5 amperes. So now what will happen is, once we make the switching, because of the series circuit, the current in the circuit is constrained to be the same everywhere, right? Because there is no device that stores charges, or there is no other path for the current to move. So of course the current everywhere in the series circuit has to be the same. So the rule that we always go about preaching, that the current through the inductor before and after switching does not change that much, or does not change at all, is going to be wrong here, because here the current will instantaneously have to change because the circuit is in series. So let's say right after switching, the current is I. So the current everywhere will be I. So here in this particular situation, where you have two inductors that are attached in series to each other, here you could say that there will be an abrupt change in current as opposed to the conventional case. So basically, let's say switching took a time of delta t, which is going to be very small. Within this delta t time, there was a finite difference in the current. So which means this value is going to be very large. Which means this quantity will be very large. Okay, so now the thing is, the EMF across the inductor branches is also dependent on the value of delta I by delta t. So in this particular case, the EMF across the inductors is extremely large, okay, so as to change the current in the circuit very quickly. The main logic is, so first let's write down the general KVL equation for this particular case. So we have the battery of 10 volt, right? And the potential drop across the 4 ohm resistance, that will be negative 4I. And this would be equal to 1 Henry resistance times di by dt, and then the 4 Henry resistance times di by dt. Okay, so this is the general KVL equation. Just after switching, what will actually happen is that this thing, the time derivative term or the EMF across the inductor, these will be exceptionally large compared to the 10 volt and the 4i. Similar to how in mechanics we neglect the force of gravity for a very short interval in which a collision is actually happening, right? Now, just for the situation of 0 to 0 plus, meaning right before and right after switching, what we'll do is we'll consider the equation to be 1 di by dt plus 4 di by dt equal to 0. Okay, so we'll neglect the other two terms in comparison to these two terms. Okay, so now the thing is, if we just integrate this with respect to time, this just becomes 1 H times delta of I in the 1 Henry inductor plus 4 Henry multiplied by delta of I in the 4 Henry inductor equals 0. So basically sigma of what we're doing is sigma Li delta I in the ith inductor equals 0. So this is pretty similar to how in mechanics we conserve momentum for collisions, right? So there we do sigma mi delta vi equals 0. So this is analogous to collisions from mechanics. So if you want to draw the analogy, so this thing over here, 1h di by dt, so L di by dt, this would be like a force that is like impulsive, okay? And so this 1h dh by di by dt, so this is kind of like the force on the 1 Henry inductor. So if you integrate the force with respect to time, you get this thing, which is analogous to the change in momentum term. So the 1h dh by dt, it changes the momentum of the 1 Henry inductor, so and by an amount of 1h delta ih, and similarly this forcing term changes the momentum of the 4h inductor by this particular term, and the total change in momentum is just 0. Okay, anyway, so now all we have to do is just write down the terms. So in the 1 Henry inductor, initially the current was 0, finally the current is I, and initially it was 0. And in the 4 Henry inductor, final current is I and the initial current was 5, and this should both add up to 0. So from here I turns out to be 4 amperes. Okay, so now if the mutual inductance of these inductors were also given, and they mentioned that that shouldn't be neglected, then it will also be provided that how they are coupled. So are their fluxes mutually aiding with each other, or are they opposing? Okay, so now if they are mutually aiding, then because of this inductor's current, then because of this inductor's flux, like the 1 Henry's flux, the induced EMF on the 4 Henry inductor will be the mutual inductance multiplied by di1 by dt. And similarly, because of this guy on the 1 Henry inductor, it will once again be m times di2 by dt. I know that I1 equals I2, but we're just differentiating it because the change in current is going to be different for both the inductors, right? So yeah, now the thing is we'll once again integrate it. So di1 will be similar to is just I minus 0, and di2 is going to be I minus 5. So yeah, this is what you'll have to do if the mutual inductance is also given. Okay, so this answer would be correct, I guess. And now we have to figure out I as a function of time. So now it's just a simple LR circuit. So the solution, so we can just write this as some a plus b e to the power minus t by tau, because we kind of know that there is going to be an e to the power minus t by tau, but this is not similar to the the original LR circuit problem, right, where it was e by r 1 minus e to the power minus t by tau. It won't be like that case, because in that case the initial current was 0. So here the initial conditions are different, but the function will be the same. So it will be some a plus b e to the power minus t by tau, and tau is just L by R. So we have two inductors in series, which is 5 Henry, and two resistances in series, which is 4 ohm. So tau is just L equivalent by R equivalent. So 5 by 2 seconds. So 5 by 4 seconds. And if you put t tending to infinity here, so this term just vanishes and you'll have A. So A is the current in the circuit at infinite time. So that is just 10 volt divided by 4 amperes, 4 ohms, which is just 5 by 2. So A is just 5 by 2 amperes. Now the thing is, we can put t equal to 0. And if we put t equal to 0, this thing becomes B. And at t equal to 0, the current was 4 amperes. Okay, we are talking about right after switching. Okay, right after switching, the current is 4 amperes. So B would be equal to 4 minus 2.5, which is 1.5. So B just becomes 3 by 2. So finally, the current as a function of time is just 5 by 2 plus 3 by 2 e to the power minus 4t by 5. Okay, so C is also correct. Okay, so that is this problem. Now let's move to the next one. Okay, so this is a problem from radiative heat transfer. So we have 3 concentric thin spherical shells that are shown, and the outermost sphere can't radiate in outer space. The innermost and the outermost shells are maintained at T1 and T2 Kelvin, and assume that the 3 shells behave like a black body. So we have to find the steady state temperature of the middle shell. So yeah, that's the problem. Okay, so here T1 and T2 are maintained, and the temperature of the middle shell, I'm just assuming to be T. So of course, the idea here would be to just do a heat balance equation for the middle shell. Okay, so we'll just have to look at which all terms will be included in the incoming radiation and which all terms would be included in the outgoing radiation from the middle shell. And the incoming would be equal to the outgoing for the temperature of the shell to remain constant. Okay, so that's the simple idea. And so first, let's start from the middle shell. So the middle shell, what it will do is it will emit radiation throughout the 4 pi r square area, right? And all these radiations will be intercepted at the middle shell. Okay, so we can call this term as some Q1 dot. So this Q1 dot, we can write using the Stefan-Boltzmann law. It would be sigma times the area of the inner shell, which is 4 pi r squared, times the temperature of the inner shell to the power 4. Okay, so this is the total radiative heat transfer rate from the surface of the inner shell, and that is also intercepted at the middle shell. So now let's talk about the heat that is coming from the outer shell to the middle shell. So this is a bit more tricky, because if you observe, so if you take a patch of area dA, this will emit heat equal to sigma dA T2 power 4, right? And this will be emitted in all possible directions, right? Because it's a patch of area dA, and it will emit radiation along the 2 pi steradian solid angle, right? So now the issue here is that not all of the radiation will hit the middle shell. A fraction of it will just go back and hit the original shell, if you observe. Okay, it will be more clear if the middle shell was a bit smaller. So if the middle shell was something like this, then none of these none of these fraction of the heat will reach the middle shell. So now let's say the outer shell, it emits radiation at a rate of Q2 dot. So Q2 dot is simply sigma times the area of the outer shell, which is 4 pi into 3r whole squared times T2 to the power 4. Okay, so this is the total radiative heat transfer rate from the outer shell. So now the thing is, what fraction of this Q2 dot is actually intercepted at the middle shell? Okay, so the answer to that is, so let's call that fraction as Q2 dot prime. Okay, meaning, so Q2 dot prime is that part of Q2 dot that hits the middle shell. Okay, so this part Q2 dot, so Q2 dot prime equals some fraction f of Q2 dot. So it turns out now this fraction is actually the surface area ratio of the middle shell to the outer shell. So let's start by just quickly finding it. So the surface area of the middle shell is 4 pi times 2r squared, and the surface area of the outer shell is 4 pi into 3r squared. Okay, this multiplied by Q2 dot. So this is that particular fraction of Q2 dot that actually is received by the middle shell. Okay, let's try to feel it intuitively. Okay, so now intuitively it makes sense. So if, let's say, we make the inner shell very small, okay, then of course we know that most of the radiation that leaves the surface will come back and hit the outer shell itself. Okay, so a very small fraction of the radiation will hit the inner shell. So if, let's say, this is shell number 1, this is shell number 2. Of course, in this case, A1 by A2 is very small, and therefore a very small fraction of the heat will hit the inner shell. And similarly, if we make the inner shell very long, very large, like something like this. So then the A1 by A2 ratio will be almost 1. Okay, which means almost the entire heat from the second shell will intercept the first shell. So that's how, so intuitively it makes sense. The actual mathematical proof, I mean, for the spherical and the cylindrical case, it's very simple. If you guys want a more rigorous proof for this, you can either check out on Wikipedia. Okay, so there you can just Google the term view factor, and there is an article on Wikipedia, I believe. Or if you want to know more about this, then you can check out then there is an engineering textbook called Sengel. So you can just type Sengel heat transfer and you can go to the radiation section of it. So there is like a lot of discussion about this. But yeah, like to be honest, like it's not really in JEE syllabus. Like they have not mentioned it explicitly. So just knowing the spheres and the cylinders case would be more than good enough. Okay. So yeah, once we know it's proportional to the area ratio, then the question is simple. So if you observe the 4 pi 3r squared from the Q2 dot, it cancels out with the 4 pi 3r squared over here. And ultimately it will only depend on 4 pi 2r squared. So this thing is just sigma 4 pi 2r squared times T2 to the power 4. So this is the heat coming into this middle shell from the outer shell. Okay. So now the thing is, if we look at the middle shell, of course we have the inner shell emitting rays outwards, which reaches the outer shell. So this heat transfer rate once again is equal to, so let's say that is equal to Q3. Okay. So that is simply sigma 4 pi 2r squared times T to the power 4. Okay. And we also have the inner shell of the middle shell radiating heat into the first shell. Okay. So if you observe, some of the radiation will intercept the first shell from the middle shell. And okay, so now here we have to use the view factor logic, because only a fraction of the rays will hit the inner shell, and that fraction is the area of the inner shell divided by the area of the middle shell. So this plus, okay, so the fraction is going to be 4 pi r squared divided by 4 pi into 2r squared times the total heat transfer rate, which is sigma 4 pi 2r squared times T to the power 4. Okay, so these are the heat transfer terms. So Q1 dot and Q2 dot prime are the heats that are incoming, and Q3 is the total heat that is leaving. So now all we have to do is equate the incoming to the outgoing. So we can cancel out the sigma 4 pi and the r squareds. So we have 2 T power 4 plus T power 4 equals, from the Q2 prime, if we cancel out sigma 4 pi r squared, we'll have a 4 T2 to the power 4. So this will be 4 T2 to the power 4. And from this term, we'll get T1 to the power 4. I guess wait, so this would be a 4 T to the power 4. So this would be a 4. Okay, so yeah, that's basically it. So now from here, T turns out to be 4 by 5 T2 to the power 4 plus 1 by 5 T1 to the power 4, and the whole thing raised to the power 1 by 4. Okay, so this is the temperature of the middle shell. So now the question, they expressed it in this fashion. So X would be just 5 by 4 and Y is just 5. So now we can just basically add it if you want. So yeah, that was this video, guys. If you enjoy the video, make sure to like, share and subscribe. And that's it. Thanks for watching.